All right, welcome to Wednesday. Hopefully yesterday's video went off without a hitch. I did send you guys the link to the class video as well, so you can go back and watch parts if you need to help you understand those concepts better, or when you want to study for a test or something like that. Today, so we covered kind of mechanics and materials in the super high idea. We didn't get into some other really interesting stuff like fatigue, how long metal will last. I'll say a couple things about that before I move on to our final thing. So we talked about how you could take that piece of metal and bend it over, right? And it'll spring back. And if you bend it too hard, maybe it won't, way over here, it doesn't spring back all the way, right? Because it's bent permanently. Now, even if this piece of, let's say it's steel, even if you didn't bend it into the plastic region, but you stayed in the elastic region over and over and over, eventually, what will happen is it'll develop a crack right down here at the base where the bending moment, where the stress is the highest. And if you do that over and over and over, that's called a fatigue failure. It gets tired. The steel gets tired, okay? If it's not too much stress, just a little bit, you might be able to do that basically forever, okay? But when it's more over and over, that's when fatigue really starts to get at you, okay? And there's some cool math, we're not gonna try to do it, that helps predict when that happens. But I want you to realize that this is why maybe a part on your scooter lasts for 2 years. And then one day you jump the same curb you've been jumping for all these years, and it, boom, busts apart all of a sudden. And and that gives you an understanding of how that happens. Okay, so fatigue is something that I want to give you a little picture of. So this is, I'm up in a big, in one of those scissor lifts, that takes you up pretty high. And I'm at the Butterfly in the downtown Riverfront Park area. And this Butterfly, we did work on it for work. Our work ended basically where this cap finishes. So the whole mechanism with this spring and the boomerang shaped thing and the butterfly itself, that was all stuff we didn't touch, okay? I'm gonna start with that because this thing blew down a little bit after that, and we're gonna be looking at cracks that existed on this thing that developed. And so I went up in the lift to look at those cracks when they were putting it in. They had a pretty high windy day, and we wanted to see what it looked like. So I got up top, right looking down here, okay? And this is basically between the solid part of the butterfly here, that is the spine, and this whole butterfly can lift up and kind of fly, if you will, and it rotates on an axle right here. So looking down at where that axle is, tied to where the boomerangs are and the post, this is the crack that we were seeing, and it existed on both sides. Because if you can imagine, if we were looking at this from above, it looked
kind of like this. You've got this is the spine of the butterfly, so it's at an angle, and then coming off of both sides of that spine of the butterfly was this welded aluminum part, and the cracks were right here. And then through the middle of that, there's a shaft that goes to the boomerangs and ends up tying you into the main, the big mast that you see there as well. And so the boomerangs go over here, and the spring is down here, that kind of thing. Okay, so I'm being very sketchy. I just want to give you an idea of
we saw a crack here, and that crack developed either because we went all the way to the ultimate load of the material here, or because it underwent cyclical, meaning over and over loading, that fatigued it, like we were just talking about with when I was holding up my pencil and pretending that it was a piece of steel being fatigued, right? And so what's kind of cool is if we took this half here and this half here, and we split them apart so that we were looking at both halves, like when you break a rock in half and you look at the two sides, okay? They're a hollow tube. If this was fatigue, you would see, change to green, you would see markings that started where the crack started. The crack would probably start at the outside, so I'm going to show it like right there. And those markings would be very close together at the beginning of the crack. But then, as the crack got bigger and grew, you would see them get broader apart. And eventually, you'd see the crack maybe made it all the way through the material. So now the crack is actually, you'd be able to see it from the inside, from this direction, as well as seeing it from the outside, okay? And then we call them beach marks because they literally look like kind of those marks that the waves will leave on the beach. And then you hit some big load, and this net didn't get to that point because it's still sitting there. It's not in two pieces, but you'll get to this point and you wind up with just this rough face. There's no pattern like you saw with the beach marks. It's just a rough face where the material, boom, just broke apart the rest of the way. And that's where you got up to the ultimate strength of the material. You just overcame it because it had so much less strength as the crack got deeper and deeper. But if you ever look at something and you see those beach marks that look like clamshell marks, you'll know that that's a crack. And every single time it underwent the load, that crack boop, boop, progressed another level and another level, right? It started here, and then it worked its way out and out and out, okay? And each one of those represents one cycle as the crack got deeper and deeper. And so you could look at something and you could understand how it broke. Because if you looked at the crack plane and it was all just rough with no discernible pattern whatsoever, you could suggest to yourself, very reasonably, that this was not a failure due to a progressive crack with fatigue loading, but that it was more that the thing just got overstressed in one big incident. So you can imagine if you got in a car crash and something broke, there's a good chance that if you just looked at it, it would look like that, not something that had a beach mark. But if you drove across country and you realized halfway there that you are missing half of a bolt, if you looked at the half that was remaining, it might look like that. It might have the beach marks, okay, until it hit that ultimate strength point and the bolt broke the rest of the way. Just kind of an interesting thing to realize what fatigue is, and that it can occur even when you're not bending something past its elastic limit and into the plastic region. Now, one thing to realize is the farther you load something, so here's our stress-strain curve, stress and strain. If you stay in this region here, you can do it many times, okay? And you won't break. If you stretch all the way up to here, you won't get as many times before you break. If you stretch into the plastic region, right, and then it comes back, and then it comes back down to the here, so it's permanently stretched, okay? And then you run up and down this, you'll get even fewer cycles, but you'll still get cycles. In fact, you can even bend the material back, boop, the other way, so that it's straight again, but you have used up fatigue life. And you will find that when you cycle this thing around where it bends permanently and then you bend it back the other way permanently, it will not last long at all, okay? And that just gives you an idea of understanding fatigue. If something is breaking after you use it for a while, it needs to be stronger because the fatigue stress is too high. So the thing that's happening over and over and over is too high. I'm going to show you this really quickly. So the crack started on this end right here, okay? And then the crack started to get smashed together, and so it actually wore out the nice beach marks that were there. You can't see them anymore, okay? Then we got to the part where the cracking was happening. Go away. Where cracking was happening, and it hadn't had a chance to smash out yet. And you can see, look at those cool beach marks that you see. This is the pedal of a bicycle, okay? And as the damage continued, as the crack progressed further, you can see the distance between intervening rings was tighter here than it is way out here, okay? Because the crack is getting bigger, and every single time I put it under a load, that there's less section to resist, and so the crack travels further. I don't want to mess this drawing up. Okay, and then we get to the region where it broke catastrophically because it had just overloaded. In fact, when it broke, I jumped a curb, but the crack had been progressing for a long time. Look, it had made it through something like 35% of the thickness, right? Before it happened. And actually, if you look closely, there was another crack over here. There was 2 cracks developing, and you can see the beach marks right in here. So that, excuse me, that was super interesting to look at after it broke. It wasn't that fun to experience the break, but there you go. There's the piece into where it broke at my desk. Kind of a pretty interesting thing to take a look at. All right, that concludes fatigue. Okay, so that was cool. I want to move on to something that is helpful in engineering, but really completely unrelated. All right, so let's talk a little bit about drawings. Now, a lot of you like art, I'm sure. My kids love it. And if you draw something kind of three-dimensionally, like a box, you might see, you can see part that goes into the box. You can see part of the face of the box. There's angles, right? Maybe you've learned how to draw with perspective. Look at my ceiling, right? There's some cool perspective going on here. All really kind of cool stuff to draw, but not that helpful maybe to convey dimensions and how to build something. And if you looked at some drawings that maybe came with a product that you bought, or drawings for how to put something together, sometimes they're not going to be these fancy 3D things. And in fact, before we had computers, it was very difficult to do those fancy 3D things, and very difficult to do things with proper scaling, so that you could say, well, every inch you measure on the drawing is 1 foot, or every quarter inch is 1 foot, right? We would do that on drawings, and we still do today, in order to make it possible for you to measure something that I didn't put a dimension on, but I can actually go in and measure it on the drawing, and then multiply it by the factor. So let's say I measure 1 inch, and I know that it's a quarter inch per foot. So if I measure 1 inch, that's 4/4 of an inch. So that's 4 feet. So I can, okay, this thing is supposed to be 4 feet away from this thing. All right, so we use drawings, and typically when we do that, we hold the drawing in a way that we see it from one side, and then from another side, and then from another side. And think about it, how many dimensions are there? Well, we got length, width, and height, right? That's a cube, right? Length, width, and in this case, depth, right? In and out of the screen. So 3 dimensions, guess how many views it takes to convey the overall dimensions of an object perfectly? It takes at least 3 views, okay? So we're going to think a little bit about how to do that, and just kind of play around with that and help you understand that a little bit. It's used in engineering all the time, and if you're doing a little project for yourself, you're going to want to get good at drawing. So let's play with this a little bit. Let's think about another object. Okay, here's an object. If I showed you a picture and I just gave you the circle, you wouldn't know what this was. You wouldn't know how tall of a glass this was, or how, Angel's over there teasing me. You wouldn't know how deep the glass was, right? That's what we need another view for. Now, you'll notice in the case of our glass here, I can convey basically everything about the glass with just the 2 views. I can get the diameter, and the wall thickness here and the depth from those two views. Now, that actually works because guess what? As I turn this thing, the view of it doesn't change because it has symmetry around one axis. It means you only need two views, right? Because it's like one of the three dimensions doesn't matter very much, okay? That's not going to be the case for some other objects. So let's take this object, all right? So you think you know what you see right now, right? I'll turn it, and I could draw that. I'll turn it this way, and you think you know how it's shaped now, but then I need to turn it this way for you to see all the features of this object, right? If you didn't have all three of those dimensions, it would be difficult to see. All right? So, what I want you to do is get out a piece of graph paper. If you don't have graph paper, that's just fine, but hopefully you have some at home that you can grab, or you can actually make your own graph paper. And what I mean by graph paper, I mean paper that has lines that are not just horizontal, but also vertical. And I'll show you on the paper in a second, and we'll do some drawing to help us understand this a little bit better. Okay, great, we're back. And let's start with that simple object we talked about, the glass, okay? Now, if you recall, we looked at the glass from above, and it had an outer shape, right? And then it had an inner shape. Okay, so there's my glass seen from above, right? But I don't know how tall it is yet. But if I did a drawing of this, I could say that the diameter, and here's the symbol usually used for diameter, the diameter is 2.50 inches, okay? Let's erase that a little bit there, okay? And then we could also say that the diameter of the inside is 2.1 inches, 2.10 inches, let's say. All right, now we have defined this object from that view, but we haven't defined it fully yet, like I said. So we're going to come over here and turn it on its side, okay? And here's my glass. It's a short glass, all right? It has that kind of thick bottom that we saw, right? And then the thinner sides, right? And so we could dimension in this view, we could dimension how thick the bottom was. Maybe it's about, I'm looking at it, I'd say it's about 1/4 of an inch thick. All right, and let's call it a little thicker. Let's call it 3/8 of an inch. Okay, and then we could dimension how tall it is, right? And we could say, well, it's about 3.5 inches tall. Okay, so now we've kind of fully defined the glass with this simple two-view drawing. Now I'm going to do one thing here to help you picture what I was saying. Oops, I think I want that. Yeah. Put this onto a grid. Okay. So a grid can be really helpful to draw things to scale, right? So now let's take our glass, for instance, and let's think about how we would draw it to scale. So we've got an idea of it, but we haven't drawn it to scale necessarily. Let's define that 1, 2, 3, 4 of these is 1 inch. So each of these is 1/4 inch, right? From there to there, right? And that's the same in both directions. Let's think about drawing our glass. Well, we said our glass was 2.5 inches. So we're going to need, well, let's see, 2 inches. 2 divided by 1/4 is 8, right? Because there's going to take 1, 2, 3, 4 to make 1 inch, and then 1, 2, 3, 4 to make another inch, and then another 1/2 inch is going to be 2 more spaces. So we need 10 total spaces. So measure that out. One from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to go from there to there, and it's going to do that vertically as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to there. Okay, so I'm going to draw my circle really badly, apparently, like so. And then, yeah, and then we'll let it do that. Okay, now clearly I did not count my spaces quite correctly, I think. Let's make that a little smaller, okay. Oh, maybe I did, good. There we go. So, I must have been one off. 1, 2, 3, 4, 5, 7, 8, 9, 10. I was, should have been there. Okay. So the cool thing about this is if this had more features than just the inside and outside diameter, then I could draw those in and they would be, quote, to scale, we call it, all right? And when something is to scale, it makes it a lot easier to understand it in a drawing and use that drawing well. Now, I'm not going to do a perfect job here, but let's say you're doing a project at home. It can help you figure out, well, what fits in my space? You can draw everything that you do to scale and do the layout on that. And we said, how tall was this again? 3.5 inches. So we come over here. 3.5 is going to be 1, 2, 3, 4, right? And 1, 2, 3, 4, and 1, 2, 3, 4. And I didn't leave myself enough space because I said 3.5. We're going to cheat. We're going to say it's 3. All right, 3 inches. Look at that. Reality changes so fast. That's great. All right, so there's our glass. It's 3 inches tall. And I've drawn that accurately. Now, remember I said that it was 3/8 of an inch tall. So, well, a quarter is 1 square. 3/8 brings us to halfway up the next one, right? And then we've got the wall thickness here. Well, we said the wall thickness, the ID was 2.1. The OD was 2.5, right? So we take 2.5 minus 2.1. That's equal to 0.4. And then, of course, that represents the addition of 2 sides together. So the actual wall thickness is 0.2 wall, right? Because you need to divide that by 2. All right. So the result of that is we can come down here and we realize, oh, okay, I don't need quite a 1/4 inch, so not quite 1 square. And draw my thickness of this down here like that. And what I've drawn here is my glass basically to scale. Not very well there with the last one. See if we can do that a little better. Oh. All right. We're not going to try to make it snap. There we go. So that is drawing something to scale and doing it in multiple views. Now you'll notice something interesting. I'm going to switch back to the video to help you picture it, and it'll help you understand this whole thing, because what we're doing is called projected views. Projected views. Okay, so switch to video. Okay, so I got my little prop here to help us. Here's a bowl, all right? We're doing what we call a projected view. And when you're drawing an object, let's say we're drawing this pepper. When you're drawing an object in projected views, this is how you figure out how the views should be located, okay? So let's say you're drawing your pepper like that right there. All right, so that's sort of the straight on view, right? Now, if you want a top view, you've got it, you imagine it's in an imaginary bowl. So if you slid it up, it would follow the wall of the bowl and you would see the top, right? So above the straight on view is where you would put the quote top view, all right? And if you slid it in the other way, that's how you'd show the bottom view underneath, okay? And then a side view would be slid to one side or the other. Now, pepper doesn't change very much when you slide it to the sides, right? Because it's almost symmetrical around it, but you can see it's not quite symmetrical. So if you're trying to figure out how to represent something in a drawing and where to put the views, it's imagine it in a bowl and you're sliding it in the bowl, okay? And that's how you figure out where to put the views related, okay? So as I talk about drawing stuff, that's what we're gonna imagine in our minds. And I'm actually, in my mind, I think about, okay, it's in a bowl, slides up, and now I'm looking at the top. You see the bottom, right? But slide up, I'll give you my view, right? So I'm holding it here, and then I slide it up a bowl, and you see the top. And I slide it down the bowl, and you see the bottom, right? And if it's in the bowl and I slide it to the side, you see the side view, because it rolls up the side, or rolls up the other side, okay? So that's what we call projected views. Most drawings are done with imagining the object in the bottom of the bowl and sliding up towards you, okay? And there are drawings, some European drawings, that will do it the opposite way, as if the object is on the outside of the bowl. And so now when I slide up, guess what? I see the bottom, right? And when I slide down, oh, I see the top. I find these drawings very confusing. They take some rewiring in your head when they happen, but you're not gonna run into those much. And I would just suggest imagining everything like it's in the bottom of a bowl, and then as you slide the bowl up towards you, you see the top. As you slide it down the bowl, you see the bottom, right? And so on. So let's go look at the drawings again, and we'll be thinking with that paradigm in mind of projected views. So here's my straight on view of my glass, right? And when I slid my glass in my bowl, I saw the top. If I slid my glass down, then I would see the bottom, right? Now, guess what? All I can see is the flat face of the bottom, right? But I can also see what I would call a hidden line. So I'm not able to see it, but I know it's there. So I can draw a dashed line that represents the inside wall of the glass, okay? That's what we call a hidden line. And so what we could have done, in fact, I would say what we should have done on this view here, and this view here, and this view here, is we should have made those hidden lines, because the wall of the glass is on the inside. If it wasn't clear, we wouldn't be able to see it. It's a hidden line, and the same with the bottom, okay? Let's try a trickier projected view. Remember the sort of funky spoon-shaped thing I showed you? So let's draw what it looked like from the top. Again, my drawing is gonna be a little poor, but we'll say it's about 1/2 inch wide. So I'm gonna go 1/2 inch, and it goes down there's 1 inch, 2, did I count that out right? I think I did, yep. And then after that, going down 2 inches, it opens up, goes down a little bit further. Okay, comes over, goes up, back, and there's my spoon. It's a little ugly. Now we're seeing it from the top, so we're able to see the rim, right? And then that rim kind of swoops up and comes to an end like that. Now I can't tell more about the object until I slide it around in the bowl that we talked about, right? So let's start by sliding it down. Well, when we slide it down, we can see that edge and that edge, right? And we can see the front edge, but we can't see the rest. So the object, when it slides down the bowl, comes around, and we see the nose of it and its shape that it does, right? Like so. Okay. But we can't see the rest. We could draw the hidden lines that represent what it looks like on the inside, right? All right. And you could even draw the other side of this. We know that it was about this wide, right? And it came down. So now we're seeing the hidden thing on the other end of the spoon. Now, imagine we slid the spoon the other direction in the bowl. Instead of sliding it down, we slid it to the right. Well, if we did that, then we would see the shape of the handle there and the shape of the spoon doing something like this. And I realize I'm not drawing amazingly well. That's life. Sorry, guys and gals. All right, and again, we can't see the inside of the bowl, but we can draw the hidden line representing where that goes. And it kind of went up to here and then ended, okay? So I've drawn my spoon in 3 views. I can fully define it at this point. I can put a dimension on this distance right here, right? I can put a dimension on the total depth right here. I can put a dimension on its length. And notice some dimensions can be seen from more than one direction. That's just fine. Usually you can pick which one you want to put the dimension on. That's just fine. You'll notice the wall thickness can't really see from any dimension, especially if there were no hidden lines, except for the top. And normally you do not want a dimension to hidden lines. So you could dimension wall thickness right here. So let's say that's 1/4 inch. Right? And same is true for the thickness of the handle, right? So certain dimensions you can only see from one view. Some other dimensions, like overall dimensions, you'll be able to see from a couple views. That's just fine. But this helps to express fully the shape of the object. And you would want to put in, so for example, this could be the center of that radius, and you would mark what that radius was, R 1 inch. So it's a 1 inch radius there. And then you could dimension where the center of that radius was. That's why I put the little center mark there. You could also say, okay, there's a center mark for the lower portion of this bowl and a center mark for this little part right up in here. And you could see some shapes can get pretty complicated because they're a combination of multiple circles or even elliptical shapes put together. But you can understand just how complicated an engineering drawing can get, right? But they can convey a lot of information in a helpful way for a machinist or a builder to put together, okay? And it's very helpful to make these drawings to scale. It's a helpful practice to do, especially with laying things out. So let's imagine you have a room that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 feet by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 feet, okay? So there's your room. It's 10 feet by 15 feet, okay? And you want to figure out how you can lay it out. Well, if you know your bed is 3 feet by 7 feet, 1, 2, 3, 4, 5, 6, 7, right? Well, you can take that object and you can move it into the bedroom, right? You can rotate where it's at, right? Now I'm scaling it on accident, I'm not trying to. But this is very helpful to do. You can literally cut out sheets of paper that are the right size and do it, or you can do it on an electronic thing like I have here. And again, I can keep it scaled because there we are, I'm about 3 feet wide, which means I'm 7 feet long, right? And I can lay that out in my room and figure out, oh yeah, this is where I want my bed, right? And you can draw things out ahead of time. It's a lot less work to do it with paper and pencil than it is to do it in your room, shifting a bunch of stuff around only to realize when you're 90% done that it doesn't fit, right? And that's why we draw it and measure it multiple times before we cut it and start putting it into place. Excuse me, I was just moving my iPad. That spot I set it down was dirty. Okay. Let's look at a couple drawings that are more complicated. And we'll just talk through what they look like a little bit so that you can just get a feel for the kinds of things that we might put into drawings. Let's see here. I was thinking I had... Now let's look at some drawings. Here are some drawings. Here's an object. I can't tell from this view whether it's round or square. But when I look at piece 1, see how it's marked piece 1, and I come over here, oh, there's piece 1, okay. Oh, I see there's that same shape, right? And the first time I looked at that, I thought, oh, it must be a circle. But then when you see it slid up the bowl, right? So here it's in the bottom of the bowl, and then it slides up to the side of the bowl, and you get to see, oh, okay, right. The bottom lines here are hidden, right? So we're looking at the back. We're looking at this side of it here when it slides around the bowl, and I can measure the width and how big the hole that goes through it is. And I understand now it is not round, right? It's a square with 2 angled sides cut into it. Isn't that interesting? Let's take a look at another thing. Oh, that was that whole drawing. There are some other drawings in here. Like that. Okay. Here's an object. We have this is an isometric view, so it's 3-dimensional, but it's hard to dimension everything in a reasonable way. So the drafter working on this, right? He's created a plan view. That's a view from above. So that's this view here. And then he's made an elevation view. He slid it down the bowl, right? So we see it from the side. And if this was the top here, when he slides it down, this is the top here. And if you think about that being in a bowl, that's where it would wind up. Now, you do the same thing here. Imagine this view here is in the bottom of a bowl. Slide it to the side. The top is still going to be the top here. But now we're looking at that end, right? Because it has slid around the bowl. So here we are. This view here is of that end, okay? So this is how to interpret those drawings. Now, there's an interesting thing we haven't introduced you to yet, and it's analogous to cutting a piece of cake in half or slicing bread. It's called a section view. This is a section view call out right here. So this would be called section AA, and it's imagine that we slice our thing in half right here, and then we look at it from above in line with the direction of our arrow. So the direction of the arrow is basically the direction your eye would be looking after you cut the thing in half. So here's section AA right over here, and we're looking from above. It's like the plan view, but now, and see how he adds the lines in here? Those indicate that's where you did the cut. And that's what he cut through. And that makes sense here because you can see there's the tubes that he cut through. Right? And we're looking at the thing from above, and we're seeing what it looks like, not from the very top, but if you cut the top off, threw that away, and looked from the cut plane down. So now we get to see the plate that's on the bottom, which is this plate here, and it's not the same as the one that was on the top, which is why the section view was helpful for him. And then he's able to dimension where all these holes were, starting from 0 at one edge, and then a 1/4 inch from there, 1 3/4 from there, 3 1/2 from there, 7 1/2, all of them referencing back to that 0 point over there. So there's multiple ways to dimension an object. You can use this datum, the 0 datum, and go all the way, or you can measure individual values like we've done over here, 10 3/4 between those two holes. And then here he's drawn that plate with greater detail, and he's got the isometric view here. It doesn't really convey very much helpful information for him to show the other views of the drawing, so he's only given the top view. And if you look closely, this is called a bill of materials up in the corner. He's actually said what the stuff is made from. It's made from a piece of plate. The plate is 3/8 of an inch thick, and that plate is 3 by 3. Another one of these is 3/8 by 15.5 inches by 25 inches, right? And so he's stated how big the pieces are that are used, and he's stated the material here. Notice that A36, that's actually 36 KSI, or 36,000 PSI yield steel. Kind of cool, right? And he lists the weight here and how many of those pieces you need. I think that's it for this little miniature. Oh, well, that's right, we have other drawings in the set above. So we kind of start at the highest view, which is a side view of a tank. And then we get more and more detailed. And these are markups that I gave him for other information that I felt was needed to finish conveying what was there to the contractor working on this tank. Okay. So hopefully that just gives you a little bit of an idea of how you can interact with drawings. I'm going to give you a little bit of an assignment because I want you to try this. All right. Let me go back to. All right. Well, hopefully you found that interesting. I want you to take measurements of your room and the primary objects in your room. So like your bed and your dresser and your closet. Maybe you've got a lamp, that sort of thing. I want you to take those things, measure them all, okay? And I want you to create a drawing that is to scale of your bedroom as seen from above, right? And I want you to draw that on some graph paper, some grid paper. So you got to come up with a scale that fits the size of your room. So if your room is 10 feet wide, you can't make 1 inch on your page equal a foot because your page is 8.5 inches by 11 inches, and so it's not going to fit on the sheet of paper. Okay, so need to be wise, or use a bigger sheet of paper, or use a scale that works. Right? Maybe 1/4 of an inch is a foot, or 1/2 an inch is a foot. Okay, and you can just go on your squares. You can say, well, okay, there's 15 squares across my sheet of paper. I need 10 of them to represent one dimension, and I need 6 of them to measure the other. Hopefully you have a room that's larger than 6 feet by 10 feet. You get the idea. But pick a dimension for each individual square that will represent your room well enough. Okay. Now I want you to then try a rearranging of your room. So one sketch of your room is how it is set up now, and then take another sheet of paper and put the outline again of the room that's to scale, and then try drawing those objects to scale in a different configuration. Okay, and if you want to, I'm fine if you cut them out in that different shape. If you cut out another set and you try them in all different sorts of locations, all right, that would be just fine. You could set them in different locations and trace around them, right? There's a lot of things you could do. I want you to take an hour, and I want you to be creative with playing with this idea. And then I want you to do one more thing for me, which is, we're looking at your room, say from above. I want you to imagine your room slid down so you see your room from the side. You're going to need to measure how tall your ceiling is. Maybe you don't have a flat ceiling. Maybe you have a sloped ceiling, okay? So you'll want to represent that. You'll have to measure at one end how tall it is versus how tall it is at the other end. And again, I want you to draw that to scale, okay, based on how tall it actually is. And you can show me, like, where, if you have a lamp that hangs down in the room, you can show that, okay, those sorts of things. I want you to take an hour. So we're just doing 2 views, like that, all right? And when we do a little test or quiz on this, I'll probably have you try drawing a simple object. So you could do a little practice on your own of thinking about how an object would look, how you think about sliding it in the bowl, different directions, and help you understand how that's going to work. So you play with that a little bit so you get familiar with it. Grab a bowl from the kitchen, right? Grab a bowl and try it. Look down in the bowl and put the object into it and slide it and use that to help you figure out how to draw it. Okay? That'll help you do that. So your homework assignment is to draw your room from 2 views, including the objects in it, okay? And then to try a second arrangement of your room using those to scale objects oriented in different ways. And don't forget to include your door, because your door is a fixed thing in the room that you can't get around. And you can't, for example, try putting your bed in front of the door. Right? That's not a workable layout. So you got to try a different layout than that, obviously. Hopefully that's clear. Again, you have my phone number. Text me if you're having trouble, and help you sort it out. I'll see you guys on Tuesday, May 31st. I think that's Tuesday, May 31st. I hope you have a great Memorial Day. Thank you for the attention. I hope this is interesting. Do some wrestling with it, and we'll chat about it when we come back and see how you did. Thanks.